This webinar today will look at the effects of measurement uncertainty in custody transfer. It will be a good beginner's guide essentially to understanding uncertainty, putting together budgets and looking at how you may apply them in practice. So the first section will look at essentially basic uncertainty theory, various terms that are used when considering uncertainty. What does uncertainty mean? Next section, we'll look at a few examples in terms of the implications of not having appropriate measurement uncertainty and how this can cost, and hopefully drill home as to why doing appropriate analysis is important. The third section, types of uncertainty, will consider how uncertainty is evaluated. So how do we get uncertainty for a given parameter? There's different ways to determine this. That will lead us into stage 4, where I'll give a little example on how you would go through the various calculation stages in developing an uncertainty budget, and then round things off at the end with a few practical examples, which will hopefully reaffirm everything we've already discussed in the webinar. So the first thing to realise is when you make a measurement, all that is an estimate of the true value, and it does not give the true value, and the true value itself is unknown. So if you think about using weigh scales, a timer, a car speedometer, anything like that, all that device is doing is making an estimate of what the true value is. And that, whatever device has been used, it will have an associated uncertainty. So what is uncertainty itself? So it's defined as an interval either side of the measurement result where you'd expect a given value to lie, or the true value to lie, with a given confidence. So if you look at the figure, you've got an indicated value here from your device. You have an uncertainty around that. So you think it may lie, you're saying your device is measuring this. We think it may lie, the true value may lie to either side of this. And as you can see here, the true value lies within these uncertainty bands that you're quoting. There's also confidence level as well. So this is a likelihood a real value of a measurement will lie within a specified interval. If you have a larger interval either side, it's pretty obvious you're going to have a higher confidence that the value will lie within it. So this is probably one of the most important things from this webinar. When you are stating uncertainty, the 3 things you must always state is the value you've measured, the uncertainty in that value, and also the confidence level in the stated uncertainty. So as it says here, the result of a flow measurement could be stated as 3.5 plus or minus 0.2 litres at a 95% confidence level. So in practice, what does that sort of term mean when you write that down? That means that you have 95% confidence that the flow measurement, the true value, will lie somewhere between 3.3 and 3.7 based on your uncertainty analysis. So essentially, based on your uncertainty analysis, 1 in 20 may fall outside that band that you're stating. Error is a term that's also used. So this is the difference between the true value and the measured result. Because the true value is unknown, in essence, the error term is unknown, but what you see commonly is that you will compare a very accurate reference with a really low uncertainty to a device under test, and you'll quote the error as the difference between the indicated value from the highly accurate reference and the device under test. Accuracy is a term that's used interchangeably with uncertainty. So accuracy is defined as the closeness of agreement between the result and true value. You can have an accurate measurement with a large uncertainty. So in a sense, you can have a device that has a large uncertainty, but you may get lucky with one particular measurement and it is close to the true value. What's important is that you can't attach a value to accuracy, and it's a qualitative term. So you may describe an instrument as being more accurate than another instrument, but when you assign a value to accuracy, you're really talking about uncertainty. And then when you talk about uncertainty and give an uncertainty value, you need to give an associated confidence level with that. Repeatability, that's another term that's used. So that's how close the agreement is between successive measurements under the same conditions at the same time. And it gives some examples of these conditions. I won't read them out, but this is something typically where we have a flow meter in one of our flow measurement facilities. We'll do a test point for a given period of time. As soon as we finish that test point, the gas keeps flowing or the liquid keeps flowing, and we'll do another repeat measurement. And we'll do this over and over to get a sense of the repeatability of a device. So a few definitions. If you have an accurate device, it is by definition repeatable, because if it's accurate, it's always close to the true value. And to be always close to the true value, it needs to be repeatable. If your device isn't repeatable, it's going to ultimately mean it's not an accurate device. As I said before, you might get lucky with a measurement that it's close to the true value, but in general, it's not going to be an accurate device. You can have good repeatability. So in the bottom left, you can have good repeatability from a device or any measurement process, but it doesn't necessarily mean it's accurate and close to the true value. So this leads us into bias. So this is when every measurement is affected in the same way. You have a relatively repeatable device here, but it's affected by bias. You can correct for bias, but you need to consider the uncertainty in the correction you're making. So just a few examples in terms of scale and how it is important to reduce uncertainty for given processes. So from 2022, there were around approximately 81 million barrels of oil produced per day. And if you assume $89.79 per barrel, that's approximately $7.27 billion per year in oil, per day produced in oil. If the uncertainty in the amount produced, based on the flow meters used, is 0.25% at 95% confidence, that gives a financial exposure of £18.2 million per day, which isn't an insignificant amount of money. So what this means is that you've got 95% confidence that you'll not be exposed either way, greater or less than £18.2 million per day. So essentially there's a 1 in 20 chance that it might be more or less than 18.2 million. A more relatable example is looking at petrol stations and the flow meters used there. So if you have a capacity of 50 litres for a fuel tank and the uncertainty is 2%, that gives an uncertainty in filling the tank of 1 litre plus or minus, or at a 95% confidence level, I should say. And if you assume £1.45 per litre, in terms of filling a tank, that will be £72.50 plus or minus £1.45 at a 95% confidence level. If you assume 1 fill per week, so multiply your 1.45 by 52, you could be exposed. It says it's exposure of up to £75.40 at a 95% confidence level. So again, what this means is there's a 95%, based on your uncertainty analysis, there's a 95% chance you won't be exposed, so you wouldn't lose more than £75.40 or gain £75.40, and it's likely that you're going to be within that amount of money in terms of how much you lose or gain based on the accuracy of the flow meter. So now we can look at types of uncertainty and uncertainty analysis. So it's generally divided into two types. The first type is using real data and analysing the real data to determine the uncertainty values. And then generally the rest of the uncertainty, type B, is anything else where you're not using statistical data to derive it. So it might be on a specification from a manufacturer, calibration certificates. You may need to use your own judgment. and experience to determine, almost guess what a value is in some cases in the absence of information. So if we look at type A analysis initially, so what I would say is a lot of the information here and in this webinar, particularly for type A uncertainty, comes from what's called the GUM. So that's the Guide to the Expression of Uncertainty in Measurement, and it's almost the standard for how you analyse uncertainty, how you derive uncertainty values and construct budgets and treat uncertainty. So I would advise, if you're interested to learn about uncertainty in more detail, essentially, I would read through the GUM because it's quite a detailed document in terms of uncertainty analysis. So type A analysis, essentially it's analysis of repeat measurements. If you repeat a measurement, it reduces the chance of an error. The repeats never tend to agree. From there, how do you decide which value to use when you've got a lot of data from different values in terms of repeats? And then what does that variation from each measurement tell us, essentially? So in terms of estimating what the true value is, the best way to estimate a true value, if you've got a raft of measurements, is using the average. So in this case, there's 10 measurements between 73 and 74 from a flow meter. The best estimate is simply the average of the points. So next step, if you want to try and do something to characterise how spread out the values are, one option would be to use the range, so simply subtract the lowest value from the highest value. But the problem here is that ignores the majority of the data. So the best way to characterise the spread of data is using the standard deviation, and we can show this with an example. As I said, if you take 10 readings of a flow of oil and get the results in the table below, we can then start to evaluate the standard deviation. So in each of the forthcoming slides, there's a little red box in the equation, and it shows what we are evaluating in each slide. So to calculate the standard deviation, the first thing we do is we calculate the average of all the points, which is 73.52. We then take each of the flow measurements and subtract the average from this value. So for all the flow measurements, we've then subtracted the average, and that's what gives us this difference in the green row at the bottom. From there, you square the difference. So again, in the sort of yellow-orange box at the bottom, row at the bottom, that gives us our squared values. And then the next step is to sum all of those values, which gives a value of 0.576. The next step is to divide by n minus 1. So that's the number of measurements. So 10 minus 1, 9. And then finally, you take the square root, and that's how you calculate the standard deviation at a value of 0.253. So what the standard deviation does is it defines a bandwidth around the average value that you've calculated where you might expect the true value to really lie. As it says here, the standard deviation, all that is an estimate of the true standard deviation. What we're trying to do is characterise a standard deviation of a full population of dataset when we've only got 10 values. As it says, it's based on a limited number of samples here, n. The more data you can base it on, the more reliable your estimate will be. And essentially, how reliable it is depends on the degrees of freedom in which it's based. So in terms of degrees of freedom, so that is what our n-1 term is in our denominator. So that's the number. It's defined as a number of independent observations under a given constraint. So in terms of our constraints, the only constraint we have is that all of the 10 deviations from the mean sum to 0. That's the only constraint we have. So in calculating degrees of freedom, there's 10 readings and there's one constraint. So we've got 9 degrees of freedom in this case. So if we took 1,000 or 10,000 measurements, we would have a lot more degrees of freedom. That would mean essentially we would have a significantly lower standard deviation because we're essentially more confident in the spread of the data because we have so much more data available to us. So the more and more data you get, the more you reduce your standard deviation based on the degrees of freedom. So what that standard deviation does is it describes what the estimated uncertainty would be if you made one reading. But you make multiple readings, and what you want to look at is how confident are you in that average value. So you need to take it a step further. So the standard uncertainty in the mean value that you've calculated, not just a single reading, is your standard deviation that we've previously calculated in the slides, divided by the square root of the number of readings, and in this case 10. And as it says, more readings, you get more confidence and essentially a lower and less uncertainty. So the next step is to take the square root of our previously calculated value, and that gives us a standard uncertainty in the mean of 0.08. So when we look at this in terms of our measurements of oil flow rate, we have our 10 measurements here. The reason standard deviation is so high is we don't know how this will take shape in a sense, but if we gathered more data, you would see a pattern emerging over time. And this is a very common bell-shaped normal distribution curve you see for a lot of things like people's heights, people's weights, a lot of things in nature gather around this normal distribution curve where most people are average, and then you tend to drift off towards, or the distribution tails off towards the extreme, and the frequency of, or the chance of that occurring decreases. So yeah, this is a normal distribution here. So what the standard uncertainty is it's defined as the uncertainty at the lowest confidence level. The likelihood of finding a true value in this interval is 68%. One standard uncertainty is equivalent to a standard deviation. So what we've calculated there, standard uncertainty in the mean or standard deviation for one value, there's 68% chance that within those bands we would expect the true value to lie. Typically, things are stated as an expanded uncertainty. So it says here the likelihood of finding a true value in this interval is higher at 95%. So to get that, we would multiply by 1.96 to expand the uncertainty. So what we're doing is we're saying we want to be more confident in the result, so you'll need to increase your uncertainty limits essentially. So now we can look at type B. Essentially, we don't always have a raft of experimental data to do statistical analysis on. So in a sense, you sometimes need to do it from other sources. You might need to, as it says here, you might need to use your judgment. You may just get a data sheet from a manufacturer that says this is the uncertainty, this is a confidence level in the uncertainty, and similarly for a calibration certificate. So we produce calibration certificates and give them to customers, and we'll say this is the uncertainty for a particular test, this is our confidence level. You don't need to do any data analysis, just we've did all that, take the value and build your own budget, however you want to build it. So most of the time they're stated at a 95% confidence level, and then from there you use the coverage factor K as a divisor, and then you transfer back to standard uncertainty U for the purpose of a calculation. So here, yeah, whatever expanded uncertainty it's at, you would divide by K, whatever the appropriate coverage factor is, to take it back to this standard uncertainty at a 68% confidence level. It says here, you get different types. The first one is the normal distribution. We've spoken about this before. If you want to go from an expanded back to a standard uncertainty, there's various coverage factors on the right-hand side of this curve that you would divide by to get back to your standard uncertainty. Sometimes it may be given as K, so you may have an uncertainty value quoted and it doesn't give a confidence level at like 95% per se. It will give K equals 2. So sometimes you'll get it as K equals 2, or a lot of times you'll get it at a 95% confidence level. It just depends. But you need to, if you get it at a confidence level, you need to get K from a table, a lookup table, and divide by the appropriate coverage factor. So we've only spoken about normal distributions so far, but the other sort of common distribution we typically use a lot is a rectangular distribution. So for a normal distribution, we take credit for the fact that although there is a distribution of values, there's a greater chance of the value being at the average. And as you go further out, there's less of a chance at being at the extremes. However, for a rectangular distribution, we are saying we know the value lies between two limits, but it could equally be right at the limit as opposed to between the limits. So a standard uncertainty, to calculate a standard uncertainty in this case, it's the difference between the limits times a half divided by root 3. I won't go into the derivation in that, but if you Google it, you'll find a derivation in terms of how to do that and why it is divided by root 3 times half the limit. So an example of this is resolution uncertainty, and this sort of makes it clear as to why rectangular distributions are used. So if we've got a flow meter and it's measuring 35, really the value that it's measuring could be anywhere between 34.5 and 35.5. It could equally be right next to 34.5 or very close to 34.5, as it could be right on 35. So we need to assume a rectangular distribution in this case. So to calculate the resolution uncertainty of this device, you would take the difference between the two limits, times it by a half, and divide by root 3. And that gives a standard uncertainty of 0.29. If you want to reduce the uncertainty, you could increase the resolution of the flow meter. So now it's reading 35.0. So now in this case, the value that's been registered by the flow meter could be anywhere between 35.05 and 34.95. So if you go through the calculation stages again, you get 0.029. So you've reduced the resolution uncertainty by a tenth, which makes sense because you've added another decimal place to the flow meter. So now we can look at just a few slides on calculation stages that will lead us into the examples we have here. So when we do an uncertainty analysis, perhaps the most important step is identifying all of the uncertainty sources that feed into it. You know what your output parameter is you're trying to calculate the uncertainty of. Do you use an equation or something to calculate this? So you need to identify all the sources that feed into this and think about all the permutations that could cause there to be uncertainty in this measurement or calculation. The next step is to estimate the magnitude of all the sources. You then convert to standard values. As I said before, it might be in expanded uncertainties or give a K factor. Typically, for treatment of uncertainty and uncertainty budgets and calculations, it's better to get things back to a standard uncertainty. From there, you calculate what's known as a sensitivity coefficient, and I'll touch on this in the example, but it's essentially how sensitive the output parameter is to whatever uncertainty parameter is you're currently treating. Convert to output values, you're at this stage you multiply the answer from stage 3 and 4 together. You multiply the standard uncertainty by the sensitivity coefficients. Correlation I'll touch on later as well, but that's how related certain uncertainties are to one another. Combine using the appropriate method. So this is advised in the GUM. It's essentially looking at what's called the root sum squared method. And again, we'll go into that in the example in terms of how you combine uncertainties together. Express at the correct confidence level. So whatever confidence level you want to express at, 95%, k equals 2, k equals 3. You can express it any way you want. And then finish off. And that's you essentially finished off your uncertainty analysis. So if we look at a few practical examples. So if you look at an orifice plate, which for those of you who don't know, I assume a lot of you will, it's a differential pressure flow meter, where the flow rate is proportional mostly to the differential pressure across the plate. And as the differential pressure across the plate changes, the flow rate changes. So the mass flow rate through the device is shown in the box below. I wouldn't concern yourself too much for this equation per se, but if we're trying to work out the uncertainty in the mass flow rate, Q, we need to understand what the uncertainty is in all these parameters and how do you go about doing that. So if we take all the values in the equation and we assign them a value and they have a value, we can calculate a flow rate based on that. So it's coming out here, based on all those values, the calculated flow rate is 100 kilograms per second using the equation in the page before. So now we've identified all our parameters that feed into our uncertainty budget. So in this case, we're looking at our calculation. We're saying we know all of these parameters that are used to calculate the mass flow rate. They may have an uncertainty associated with them. We've identified them. We know what the value is. And now we need to define what the uncertainty value is. So if we look at discharge coefficient and expansibility factor, the uncertainty may be stated as a percentage. Pipe diameter and orifice diameter, that's stated as an absolute value in this case. Pressure drop and density, so the red boxes, they're highlighted in red here because if you think about it, if we go back to the slide previous, pressure drop is calculated using this YouTube manometer. That will have a calculation itself, so the pressure drop will be calculated by rho, the density, acceleration, gravitational acceleration, and the height difference in the YouTube manometer. So particularly the height and the density of the fluid will have an uncertainty. So there'll be a separate uncertainty calculation prior to this to feed in and give us this value of 100 pascals in uncertainty. And it's the same case for the density of the fluid in the inlet. It's got an uncertainty here of 0.3%, but the uncertainty and density, that may be based on the equation of state, which is used to determine the density. You will have a temperature and pressure measurement. That will have an uncertainty. So there'll be separate uncertainty calculations that feed into this current budget. But we've now completed stage 2, so we've got all our uncertainty values as expanded uncertainties, whether they be calculated previously, they be quoted in a percentage term or absolute terms. But we've got all our values that are important for this budget. Stage 2 to stage 3, we are simply going from an expanded uncertainty to a standard uncertainty. So some things will be at k equals 2, so the uncertainties may be quoted at k equals 2, wherever we've got them from. Pipe diameter and orifice diameter, these are divided by 1.73, which is root 3. And the reason for this is that, particularly pipe diameter and orifice diameter, that these will be manufactured to a tolerance. So if they're within that tolerance, they will essentially be accepted. So there's just as much a probability that it's right on the limit of this tolerance, that or it's right at the value of 0.5. So we we're reluctant to take any credit that there's more of a probability that it's at the middle of a normal distribution as opposed to a rectangular distribution where it's on the edges. So instead of dividing by 2, we divide by root 3, which is 1.73. The impact this has is it increases the value in the column under small u, or 3. And it's just slightly conservative because we're saying it may be more likely to be at the extremes than in a normal distribution. So if you're unsure of something, whether something's a normal or a rectangular distribution, and what's best to assume, sometimes it's best to assume a rectangular because it's just a little bit more conservative for the uncertainty analysis. So now on to stage 4, which is calculating the sensitivity coefficient. All this is it's looking at how sensitive the output parameter is if you change the input parameter a little bit. So a way to do it would be you could partially differentiate. So for discharge coefficient, you could partially differentiate dq by dc, the c discharge coefficient. If the equation is simple enough, you can do it, and you can evaluate what the value would be for dq by dc. Sometimes the differentiation gets a little bit complex in what you can get away with doing. In the case of discharge, if you looked at the discharge coefficient, we would use all of the values that are already given, so the true values of the parameters. But for discharge coefficient in the equation, we would use 0.6 plus or minus plus 1 standard uncertainty, so 0.6 plus 0.0015, and calculate the flow rate. So this would increase the flow rate a little bit. We would then do the same, but we'd actually subtract 0.015 from 0.6 and calculate the flow rate again. And then we would look at how the flow rate, what the change in flow rate, the difference in flow rate from using the different discharge coefficients are. We're essentially dividing the difference in flow rates by the difference in discharge coefficients used to calculate the flow rate. And that gives us what's in column small c. We then multiply u by c, and that gives us our uncertainty and our output units of calculated flow. And then the next stage is to combine them using what's called the root sum squared method. So the way this works is that it essentially takes credit for the fact that the uncertainties may be at different points of the distribution. One uncertainty may be at the top of the distribution and increase the calculated flow, and the other may be at the lower end and result in a decreased calculated flow. So we're taking credit in this root sum squared method for the fact that different uncertainties may be at different points of the distribution, and therefore it wouldn't be suitable adding all the uncertainty values together. Because if we added, so if we look at column 5, the purple column, if we added all of them together, we wouldn't get this 0.267. The way we get the 0.267 is square each of the UC values, and we've got our UC squared column. We sum all of those values down to get 0.0711, and then we take the square root of that, which is less than we would get if we added all the UC columns together. And what we're doing is taking credit for the fact that if there's an uncertainty in a certain value, it might be pulling up the calculated flow, and if there's an uncertainty in another value, it may be pulling down the calculated flow, and that's essentially how it works. So now we've got our UC term at the bottom of 0.67. We work back the way to get our calculated uncertainty. The sensitivity coefficient is 1 because it's already in the appropriate units. We can then multiply by whatever coverage factor we want to use. In this case, we're multiplying by k equals 2, and that gives us an uncertainty and calculated flow of 0.533 at k equals 2, which is a confidence level just above 95%. So what we're saying by our result there is that there's a 95%, we're saying there's just above a 95% chance that the true value lies somewhere between 100 minus 0.533 and 100 plus 0.533. So another example is We can look at the volume of a tank. To calculate this, your governing equation is the volume of the tank equals pi multiplied by the diameter of the tank squared multiplied by the height and then divided by 4. It may be the case that you measure the volume of the tank, you take your height and diameter measurements at a different temperature other than 15 degrees C. And because the tank expands and contracts under temperature, we want to standardise the volume of the tank for 15 degrees C. So from there, you would divide your measured volume based on the equation in the previous page by 1 plus the alpha, which is the thermal expansion coefficient of the tank, times the temperature you measured it at minus the 15 degrees you want to standardise the volume of the tank at. So if we look at our budget here, the first thing to notice is that in our previous example, we had one uncertainty for one parameter. Sometimes you can have multiple uncertainties for one parameter. So if you look at the diameter, there's a calibration uncertainty. So this might be the uncertainty in previously calibrating the device that's been used to make the measurement. There's the determination process. So how do you actually measure it? There's going to be an uncertainty in that. The tank diameter might drift over time. And similarly, there's other uncertainties for height. The temperature at which you measured it, to correct for it, you're going to need to measure the temperature you measured it at. There might be an uncertainty in that. And also how the tank expands and contracts, that will have an uncertainty associated with it as well. So again, I won't go through this example, but we do it the same way again. We've identified all of our expanded uncertainties. We divide by the appropriate K factor, so whether that be divide by 2, whatever value, some are root 3, so we've assumed a rectangular distribution in some cases. There's the standard uncertainty. We then calculate our sensitivity coefficient and then our UC term. We do the root sum square method, so we square all of the purple values and then sum the squared values together. And then from there we take the square root and then express at the appropriate confidence level to give an uncertainty of 3.188. So uncertainty analysis is very much an iterative process. You can to achieve this uncertainty, and then we calculate what the uncertainty calculate or predict what the uncertainty would be. We'll do our uncertainty budget and our uncertainty calculations, and then we might think, oh, our uncertainty is too high. If it is too high, one of the things we can do is to look at what the largest contributor is. And to do this, it's probably best, or it is best, to look at the largest UC squared term in the budget. So if we want to reduce our value in this case from 3.188, we know the calibration of the device used to determine diameter is the largest contributor to uncertainty. So we could look at reducing this, and this will have the largest impact in reducing our overall uncertainty. So if we halve this uncertainty, this would reduce the overall uncertainty down to 2.72 from 3.188. If it's still not low enough, you just move on to your next term. So in this instance, it's a calibration uncertainty in the device used to determine the height. If you reduce this again and half this, you reduce the uncertainty further. And then again, it's looking at the determination method of the diameter. If you reduce this, you can continually reduce your uncertainty. So that's uncertainty budgets are very iterative. You define what you want your uncertainty to be. Initially, you put a budget together. If it's too high, you need to look at what the main sources are and whether you can reduce them. I did speak before about correlation and combining uncertainties. The way the root sum squared method works, as I said, is it takes credit for the fact that things can be at different points in the distribution, and if you have enough things, they can almost cancel out. So in this case, you've got two separate flow meters. One's overreading, one's underreading. So you can combine the uncertainties by squaring the uncertainties, adding them together, and taking the square root. This gives a lower value than simply summing U1 and U2 together. However, if you're using 1 metre to determine the combined flow, it's going to be under-reading for both or over-reading for both, typically. So using the root sum squared method here isn't appropriate because it's going to give you a false value that's lower than what the true uncertainty is. And for correlation, typically you would add them together to see what the impact is. The GUM goes into this in a lot more detail about partially correlated uncertainties and how things can be partially correlated. But as a good first pass, adding correlated uncertainties together as opposed to root sum squaring them is a good way just to check what the impact is if you've got a hunch something is correlated together. You want to make this as simple as possible. If you don't need to go into the detailed correlation, it makes things a lot easier. So we can look at this as an example. So suppose, again, back at the tank volume example where our uncertainty is 3.188. If you've got two devices, let's say you're determining the diameter and the height with two separate devices, but the devices were both calibrated at the same calibration house. In this instance, if the calibration house is out the same way, it's likely going to be out the same way. So it's probably best or more conservative to assume that these two calibration uncertainties are correlated. So in this case, instead of squaring each of those UC terms, you would add them together first. So you're adding 0.955 to 0.905 and then subsequently squaring them. From there, you would just work through the process again by summing all of the UC squared terms together and working back through. And as you can see here, it results in an increased uncertainty. And that's essentially because you're not taking credit for the fact that they may be at different points in the uncertainty distribution. You're assuming they're essentially at the same point in the uncertainty distribution. You can't take credit for that. So just in summary, in terms of handling calculations, as I showed in the examples, it's always easier to convert to standard uncertainty. Things can be quoted in different confidence levels. You might have different distributions, so it's best to get back to standard uncertainty. Just as you do with calculations, whether you use SI units or any other units, you just need to make sure everything's in the correct units, as you would with a calculation. Be conservative and tend to always round up. And these can sometimes be large calculations on pretty substantial Excel sheets. Sometimes it's easy to make a mistake, put a wrong number in a cell. So one of the best things to do is just sense check it and ask, does this feel right? Do you have a flow meter budget that's given a 50% uncertainty when you think it should be 2%? Sense checking it against what you think it should roughly be is always a good idea. So just in summary, measurement itself is meaningless essentially if you don't have a statement of uncertainty in the associated confidence level, because that's essentially what's giving you the quality of the measurement. It's defining how good your measurement is. For certain applications, assessing uncertainty can be time consuming and require careful thought to consider what all your sources are. But if you do the analysis correctly, it will save time and money in the long term, particularly for high value applications. So yeah, I'd just like to thank you all for taking the time to attend today, and I'll pass you over to Russell.
Yeah, thank you, Dale. That was very interesting. Now, I've got a good number of questions here for us to run through. So first of all, how would you make a start in developing an uncertainty budget?
Well, if we go through the stages again, I think the most important thing is to understand what you're trying to calculate the uncertainty in, and then subsequently, if there's any calculations that feed into the thing you're trying to calculate. So you need to almost work back the way from what you're trying to calculate and work back the way as much as reasonably practical. So again, for the orifice plate, you know what your output parameter is. You're looking at what feeds into that and then working back the way. And then something that's probably the most important doesn't really require knowledge or massive knowledge in uncertainty, is understanding the process. So sometimes you may need to speak to people that have no knowledge on uncertainty, but they know the process really well, and they can define uncertainty values better than you. So it requires a knowledge on uncertainty to develop the budget, but it does require people who know certain processes to understand what the parameters are and what the values should be, particularly for type B analysis.
Okay. And how often should you review your uncertainty budget?
As and when required. There may be things that, so a lot of instruments can drift over time. That doesn't necessarily mean you need to review them all the time, because you can put uncertainty terms in there. But if you make any major changes to your measurement process or the way something works, you would need to consider reviewing the uncertainty budget. So you need to essentially look at all the parameters that are in your budget. If any of them change, if you can reduce the uncertainty, but if some increase. There's no set time. I wouldn't say there's any set time you can define as to how often you review a budget. It could be weekly or it could be yearly, just depending on how variable your process is.
Okay. And why are uncertainties commonly stated at 95% confidence level?
I think it's just for ease of understanding, because standard uncertainties are around a 68% confidence level. What you're essentially saying there is that 32 in 100 measurements will be out with this stated uncertainty, where it's just easier if you state it as a 95% confidence level, that basically means 1 in 20 is outside these limits, or 99%, 1 in 100 is outside these limits. So it's just more easy to wrap your head around.
Okay. And how can you get hold of a copy of the GUM, or the Guide to Uncertainty Measurement?
It's available online for free. So if you type in GUM, Guide to Uncertainty and Measurement, I think you can find it. One of the first few links in Google will probably give you the option to download. It's free.
So that's good to know. It's free and easy to access. So you say that when correcting for bias, you need to consider the uncertainty in the correction. How would you do this?
So if you have a bias if you have a bias that's under reading or over reading, if you take multiple measurements of the bias, and you would evaluate it the same way we showed in this webinar, you would calculate the average bias and then work out what the standard deviation is, and then the standard uncertainty of the mean bias, and that would give you essentially an uncertainty in your correction factor that you're using for the bias.
Okay. Just sorting through this, a lot more have just come in as we finished. So yeah, apologies to anyone that we don't manage to answer. We'll try and respond in the next few days if we don't get to your question. How many data points do you feel you'd need to take to qualify the repeatability?
Typically, we take 3 to 6 in terms of repeatability, but it doesn't. It will give a good sense of what the repeatability is, but it won't improve your repeatability. The repeatability is almost inherent to the device. The more measurements you take, you're going to get more certainty in what the repeatability is, but it's not going to improve your repeatability of your device. You're balancing it against time for calibration and cost to determine the repeatability of device. 3 to 6 points typically you take in full measurement calibrations.
Okay. So here's one here. So calibration uncertainty seems to be key. How do you quantify the uncertainty due to the calibration period? Frequency of calibration or etc.
So could you repeat that, Russell? Is that how you quantify the uncertainty in calibration?
Yeah, how do you quantify the uncertainty due to the calibration period? So say, I presume one instrument might have a longer calibration period or is calibrated more frequently than another. How do you include that?
Yeah. So typically we include a drift term for our devices, whether that be, it can be any device such as a platinum resistance thermometer or a flow meter. It will be calibrated with, you'll get your calibration certificate from the lab to say this is what we think the uncertainty of the device is at an appropriate confidence level. But if you have, for example, calibrated that device yearly for 6 or 7 years, you're going to have history of its drift. I mean, if you've got history in its drift, you can estimate a reasonable uncertainty in how it's going to change, its performance is going to change over the next year before its next calibration period. And you can use that to add an uncertainty term to your budget. I hope that answers the question.
Yeah, hopefully, I think that does. Are there any situations where you might come across a higher confidence level, say the 99% confidence level?
Most of the things we see in terms of looking at them, type B analysis and non-calibration certificates, they're just generally quoted at K equals 2 or 95%. Sometimes, rather annoyingly, you don't even get a confidence level stated, and you have to just assume that it's at 95% or K equals 2. You can state it in an increased confidence level if you want to understand what the difference is in terms of uncertainty for the chance of it being out 1 in 20 times or 1 in 100 times, how you need to increase your uncertainty. Some things you might want to quote things at a 99% confidence level to be more certain in your uncertainties. Yeah.
Okay. I think we might have time for one last question. If you have an instrument that has poor resolution, what would you suggest is the best method for determining the measurement uncertainty of this device?
If it's got a poor resolution, what's the best method?
Poor.
Is that it?
Yeah. Yeah.
If you're testing a device that's got poor resolution, the first thing is to confirm it has poor resolution. So if you have a budget for it, if the resolution uncertainty is higher than anything else, so your UC square term is higher than anything else, doing low uncertainty calibrations is probably going to be pretty worthless because your uncertainty and resolution is so high. So if you're trying to reduce your uncertainty, your overall uncertainty in the device, you would need to have quite a good resolution to that. and allow the other components of uncertainty to have more of an effect. So you really want to minimise your resolution uncertainty if you're trying to have a low uncertainty device. Hope that answers it.
Yeah, hopefully. Well, thank you for your webinar and for answering your questions, and thank you everybody for joining us here today. As I said, if we haven't managed to answer your question, we'll try and respond. And if you have more questions, and Dale's contact details are on screen. As I also mentioned earlier, you will receive a link to the recording of today's presentation, as well as the slides that are on screen. Please get in touch with us if there's any webinar subjects you'd like us to cover in the future. It's great to hear exactly the sort of topics that you're interested to learn more about. You can get in touch with us or send us any details or queries at info.uk@tufsud.com. You can also visit our website for more information, which is www.tufsud.com/UK for more information. So, on behalf of myself and Dale, thank you for your time and enjoy the rest of today.